Hey, how's it going? All right, Thursday. Welcome to class. We have, so before we get in, there's a bit of housekeeping. I just want to talk through, I posted a description of the final project, just to get you all thinking about these things. We have about a month left in the semester, and it's a good time to start thinking about pulling together this project. This is not the kind of project that you can do overnight. So I want you to be thinking about it early. We'll talk through some checkpoints leading up to the project, just to get you thinking about these things. The first thing to do, and I have a due date for this. The first thing to do is to pick your group. So find some people who might have some similar interests and who you can trust to work with. Group projects are always a little complicated. So make sure you're feeling comfortable with the people you're choosing. And if you don't want to choose groups for yourself, I can assign you groups as well. So if you're not close with anyone in the classroom, I'll give you some people to work with. So the first thing I want to show you is the project description. So this is posted. This is just some guidelines for what we're doing. Essentially, the main objective of the final project is for you to demonstrate your skills with the things we've been working with. So particularly part one, so working with data, and then what we're doing in part three, which is essentially performing tests with data. And then in the last part, we're going to sort of pull these things together. So the project is primarily based on, we're going to talk sort of more in depth about the types of things we'll be doing in the final project in the last part of the semester. So once we get through essentially regression, which we'll hit next week. So you'll be using like real world data and doing exploratory data analysis, the type of approaches we were taking in part one with visualization. And then you'll be working to express and communicate your findings to the classroom. So in the final class period, the final exam period, we're going to be doing some presentations. So we'll bring some snacks and coffee, and then you'll tell me some interesting things you've found using like 1 or 2 slides. It's going to be very quick. We have a lot of people in this class. So there are some example data sources that I have here. So you can use one of these. I'll also post some more examples of data sources to Canvas. I might also post them to the part 4 page when that's up. But you can also use other types of data sets. So if you have something particular that you're working on in other classes and you want to sort of approach it from a data perspective, this is a good chance for you to do that. If you have a choice between doing something specific to economics or doing something specific to something you're interested in, I would prefer you do something a little different than what most people are doing, but is interesting to you. So you tailor the project to what you're particularly interested in. That's what I would hope for you. But I'll give you some suggestions as well. So the main requirements, the first is that you do an exploratory data analysis. So we're like describing what the data is showing, and then so I was hoping you were able to see this. So this is a Word file. So this is a document you can download from the Part 3 page at the moment, just under final project description. And then this is the overview data selection. So I have a couple of examples here. And then the requirements are exploratory data analysis, so like summary statistics, some data work, and using visualizations. I'm hoping for at least 2, and probably not many more than 2. And then using some of the approaches we're developing at the moment. So thinking about probability distributions, thinking about hypothesis testing, which is what we're about to start on Tuesday. And then regression, which we'll hopefully start on Thursday. And then can you describe what you're doing? Some of the insights, some of the things that your data is showing. So can you work with the data, and can you communicate with the data and communicate its importance? And then I'm looking for a presentation for, like I mentioned, in the final class period. This is like 1 or 2 slides. I really don't want more than that. And I don't actually want more than like 3 minutes. This is going to be like a very quick, sort of concise description of some of your findings, and doing it in a sort of a presentation format. So these are sort of 4 bullet points that I will be looking for. And then this is pretty short, and that's on purpose. I really don't want you doing a ton of writing, like a long document, but because it's short, to get in everything that's required, you have to be very concise. So I'm looking for, like what is it we're doing in the project? How would you describe your data? Like, where is it coming from? Some of the approaches you've taken. What are you finding? And then what does it mean? And then, so if you're using Python, I would look for an appendix with your code, or just code attached to it, and then some references, if you use external references in addition to your data sources. So then this is sort of my criteria. These are the 3 sort of parts mentioned above. And then so I've put a timeline in here so we can sort of keep track of ourselves. We're in the last month, and I just want to make sure we stay on track in terms of group work. So you can't start like the week before. Do you all like this? Do you like having a timeline with like check-ins, checkpoints? When I was a student, I always sort of felt like it was a little bit, like on one hand, it was kind of nice having someone give me a timeline. But I hope you all can like set up your own timelines at this point, and make your own progress. But I'm going to be checking in on you just to give you some extra incentive. So the first one, Tuesday, November 12th. So I'm going to be looking for you to communicate to me who your group members are. This is coming up quickly. So I'm looking for you to find some people to work with. This can be either people who you might have some interest in working with. So that could be you share a common minor or major that's not economics, and you want to do something sort of in that area of study. Or it could be a friend. You just want to work with someone who you know and you like and you trust. So be aware of and be thinking about who you might pick as a group member. You can work by yourself if you absolutely need to, but you need to let me know. I don't encourage that, and but you can do it. But you sort of need to talk to me about it. Yeah, Megan.
How big is it going to be?
Yeah, good question. So I'm looking for like 2 to 3. So the group should be pretty small. I maybe in rare exceptions I'd go with 4, but I really do want them to be on the smaller side. And then I'm going to be looking for just a paragraph description of what you're doing by the 9th. So this is a topic, a question, and then potentially a data source. So where would you be collecting your data from? There are lots of sources on the internet, and if you don't know exactly what you're trying to do, I can guide you in those ways. And then I'm going to be looking for a draft analysis early December. So you can be thinking about this over break, hopefully working on. I don't want you to do a lot of work over break. In fact, I don't encourage a lot of work over break. I want you to be sleeping, as will I. But having something written up with a figure, just so we can sort of stay on track, stay on top of these things. And then during the finals period, you'll send me your slides, and then we will I'll pull them all together, and then you'll just talk me through what you found. I'm hoping this is a little bit exciting. Part of what I want for you is not just for you to use this as a requirement for this class, but if you want flexibility to do something slightly different that's more interesting to you as a project, and maybe fits, you could do this to fit another course requirement. If there's any way I can be flexible so that this project is better suited to you, I'm willing to do those things. This can just be a course requirement for you, but it could also be in service of something else. So that's sort of what I'm hoping for. Don't hesitate to reach out over email, or if you want some recommendations for other data sources. One thing I also want to note, so I'm going to pick a few of your projects. This will only be by consent, so if you allow me to, I would love to post your slides or your figures on the ECON 0150 page, so that students in future semesters can see some examples of excellent work. I would love to do this. I like highlighting my students' work, and I'd love for you to feel good about your work and make it showable. And if you choose to let me post your work, you can reference this. So it's going to be a permanent link, and then you can reference your work on my page. So I think this is potentially a good opportunity for you if you choose to take it and like it. That's up to you, but I would love to. All right. Any other questions about this? Y'all feeling good about finding a group? I know often that's a stressful thing to do. As a student working in groups, I always hated finding the actual groups. And if you want, I can assign you groups. Yeah.
Is there the table or just?
Yeah. So it's the entire group will submit a project together. So only yes, it'll be like you'll send me an email with your file, with all of your group members attached to it. Yeah. So one file per group. Okay. Any other questions? Can I get your reaction? Are you looking forward to this project? I mean, it's like a course requirement, right? Like we have to do these things to satisfy the university. But is anyone like excited about it? Tony is. That's nice. This is the final. Yeah. So there's no final exam. The reason we're doing a final project and not an exam, most of what you'll do in communicating with data, like it will not look like an exam in real life. It'll be a slide. And so what I want you to be, I want the skills you leave this class with to be focused around communicating with data. And so we're doing a final project, which is sort of it's a better assessment type for the skills you'll use as a data analyst. So yeah, no final. Any other questions? All right. So this is one thing. Also, apologies on the delay in getting your exam back to you. I just got the result back on Tuesday. So I'm in the middle of checking it over, and it should be back to you today, later tonight. Yes, other questions?
Yeah, you probably mentioned this, but can we do the final project mainly in Python, not using Excel?
Yes, totally. Yeah, so you can use either Excel or Python. I would encourage you to use Python for the regression type skills we're about to start working with. It's also a little better with data visualization. Yeah, it's better. Python is better than Excel for those things. Yeah. But if absolutely necessary, you can use Excel. But I generally don't recommend it for most of the work you'll do. Okay. So on Tuesday, we walked through confidence intervals. We started building up this idea of using our sample with an unknown distribution and an unknown population statistic. So what if we don't know the population mean and the standard deviation? In that case, what can we say about the population mean? So that's where we are turning. And last time, I think it looks like almost everyone has already seen the code walkthrough from last time on in the recorded video from Tuesday. But we walked through a couple of examples using Python to tell us something about probabilities. So these were some of the examples, and I don't have them pulled up on the slides, but you can go back and look at some of these things. But we talked about examples 1 through 3, I believe. I guess we also did example 4 from the first slides. And I posted these to the part 3 page for you to take a look at. So you can just download them here. I've also posted the notebooks that I've used. They're a little bit hard to download for some reason. If you click on this, it'll bring up the raw. So you just have to download this and then take off the txt. So like if you download this, it will put txt at the end. Unfortunately, you have to save this and then rename it with ipynb, and then change the file extension, and then you can open it. I'm working on getting a better way of distributing this to you, but you can download the notebooks that I've been working with. It's a little more complicated than I require you to know in this class. But if you're curious about how I'm constructing these figures, this is a great place to go. So I'm giving those to you if you would like, but I know that looks a little bit intimidating. So you can also just download the slides here and go through some of these things. We did a bunch of examples, and that's what we have in our Jupyter notebook from last time. So we're going to continue working in Jupyter with Python, or our Colab notebooks. But the main question at hand today is, what can we say about the population mean if we don't know the population statistic? So if we don't know the population mean and we don't know the standard deviation, the spread of the distribution, what can we say just observing the sample? And there's going to be a bit of sort of philosophical work we're going to have to do. I'm going to show you some pictures of how to think about these things. But there's going to be one main idea and one main picture I want you to leave class remembering today. I think this is one of the most misunderstood ideas in statistics. I've said that probably a couple of times already this semester. But I hear people say the thing we're about to do. I hear people say this wrong all the time. So we're going to talk about some of the nuances and philosophical distinctions. All right, so let's get into some slides. How about? So this is what we call confidence intervals. We're also going to talk about hypothesis testing on Tuesday once we get through some of these slides. And the big caution is that I truly need you to be careful when working with these things. There's a lot of ability to be, there's a lot of flexibility for you to be wrong. So we're going to talk about some of the details and nuances, but the fundamental question, right, as we've started building up to, we're making a beeline for regression, trying to get there as quickly as we can. We're not going to spend lots of time getting into the weeds on this stuff. I need you to understand the philosophy of some of these parts, but the fundamental idea is, what can we say about the population simply observing the sample? Let's say we know nothing about the underlying parameters of the population. So this is our classic picture. We have the sample, we have information about the sample. So the standard error, or the standard deviation of the population, sorry, of the sample, and the X bar, so the sample mean. And then what we're trying to do is give some confidence, some estimate of the population. This is the thing we do as economists. Like, you know, we can sit in our leather chair and smoke a pipe, drink some whiskey, and you know, read Thomas Malthus and hypothesize about how people make decisions. That's one approach that people have taken in the past. But we live in a different world today, where to say anything about economics, we essentially always have to have some data. There are some rare exceptions, like we're simply building a theoretical model. But even in theoretical models, we have to understand something about the truth, like how people actually behave. And in those environments, we have to actually go to the data. And most of the time, we don't know the underlying distribution. So this is the most common state of the world, is all we're doing is observing a sample. We don't know the population. So we're making inferences using the sample. So we've talked about an unknown distribution. We have the sample mean distribution, which gives us a tighter standard error or standard deviation around the truth, if we were to know the truth. So we can take all samples. We talked about the distribution of this thing in these nice pictures in this central limit theorem figure. So we take a bunch of samples and we increase the sample size, and that tightens the variation around the truth. And so we get this sort of idea. And so what we're trying to do is go from the mean of X bar to or the sample to the population mean. The mean of the mean of the samples, the mean of the sample mean is the mean. This is just from taking means of things. But in general, this is sort of what we observe, right? We have a random sample, and we observe the sample mean, but we don't know where X bar is relative to mu. So like it could be in a bunch of places, and we don't know which one of these is true because we can't see it. And most of the time we will never be able to see it. So this is the big question at hand. There's going to be some sort of, I love that we have some sort of philosophical distinctions to make today. So we have point estimates, which are just like the number. We like make an estimate of a number, or we have interval estimates. And so we started talking about, upper and lower bounds, but we haven't done a lot with this yet. We've developed these models of like how we can estimate probabilities from the normal distribution if we know the underlying parameters. And we started working with intervals around the sample mean. Okay, and this gives us sort of some idea of how confident we are of the relative positions of our sample mean relative to the population mean. We're going to be sort of careful about how we talk about these relative differences. I'm going to tell you what matters, and then we're going to weaken it a little bit in practice. Okay, so we started talking about this last time. We have, or did we? I'm not sure we got this far. We did example 4, but I don't think we got to example 5 yet. Correct me if I'm wrong. Someone who watched the video, I don't think we got this far. So let's say, unlike in our past examples, we don't know that X, our random variable, is normally distributed. It could be, but it might not be. And let's say we don't know the distribution. So we don't know what the parameters are. So we don't know what mu is, and we don't know what the standard deviation is. We maybe can make some guesses, but this is the most common environment. You're like just floating off in the ocean with no true bearing. So let's say we observe for 144 days. We observe the number of candy bars that are sold from a vending machine. So we have a sample mean, but this we don't know to be the true mean. And then we have a standard deviation of the sample to be 60. So my question to you is, for a 144-day period, we're going to try to find the probability that the the average number of candy bars sold is greater than 265. Okay, so like we talked about last time, we generally do this in 3 steps. The first step is to normalize this distribution. The second is to plot the thing. And then the third is to go in and actually make the estimate. Okay, so this is sort of a picture of, you know, the types of things we're trying to think about. So we said, you know, 95% of X bar is within 2 standard deviations of the center, which we're claiming is centered on the population mean. And this is from the central limit theorem, right? So we take repeated samples, the distribution, so like the draw of X bar, is centered on the true mean, mu. So we have X bar normally distributed around the truth with this distribution. Okay. And so what we're trying to do here is talk about the probability. So our original question was the average number of candy bars sold being greater than 263. Okay, and so our confidence interval, as we've talked about before, sort of looks like this. But in this environment, you know, we don't know what mu is, and one way of thinking about the approach we're going to take in constructing confidence intervals and hypothesis testing is to guess what mu is using the information we do know, which is X bar. So far, there's a bit of sort of a philosophical background to this, and we're going to get into why we can do it this way. I remember when I saw this stuff for the first time, I was like, it feels wrong to guess. Like, why are we guessing? Like, don't we know some stuff? And how is it appropriate to guess when we don't know stuff? But we're going to talk about why this is true. This is like the main point of what we're doing today is talking about how we can do this stuff. So what we're doing is we're going to replace mu in this thing, the probability we're on this 90% confidence interval. We're going to replace this with our sample mean. And then we're also going to replace the standard deviation with our guess of the using the sample standard deviation, our sigma X bar. And so this gives us an upper and lower bound. We're using this 2 times the 5 to give us 2 standard deviations away from the guess. Okay. So this is where we're going to sort of pause and talk about some philosophy. So let's say we've done this this guess and then build the interval around the guess approach. Well, every time we take a new sample, so we took a sample just now, and we constructed an interval, but we can do this many times, and each time we do it, where we have the center point, which is the X bar, and then a distribution around that center point that we drew, the distribution will move around. We have this. We're plugging in the X bar into the distribution that we got from the central limit theorem. But because the sample itself is a random variable, that thing is going to move around. And so if the true mean is 260, sometimes the true mean will be in that interval. So the 90% confidence interval. But it won't always be. If we get a really low or a really high draw, then the interval around the sample mean will not contain the true mean. And part of the philosophical takeaway here is that the true mean, the population parameter, is not random. The population parameter is some number. We just can't see it. What is random is the draw. We can repeatedly draw a bunch of times, and each time we make a draw, it's random. Okay, so these are some of the challenges we have in practice. We really only take one sample. So what the central limit theorem was telling us, right, was it told us the distribution when we take many samples. And this is sort of where we have to sort of translate our knowledge from the central limit theorem into something we can work with. We're not taking many samples, we're just taking one. How do we work with that? That's the challenge at hand. And the reason that's a challenge is because we actually don't know what mu is. Okay. We do know that using the distribution that's given to us by the central limit theorem around x bar, that will contain the truth some percentage of the time. And this is the leap we're going to make today. It's not a leap, actually. We're going to do it sort of step by step. I'm going to build up that intuition for why we're able to do this using some pictures. The fundamental challenge at hand is how do we use the distribution given to us by the normal distribution to say something about this one sample we've drawn? These are not the same distributions. I mean, they will be in practice, but the central limit theorem isn't telling us about the distribution of the truth around the sample. It's telling us the distribution of the sample around the truth. Okay. So constructing the confidence interval, as we're about to do, will actually give us some information about the truth. This is what we call the confidence interval. Okay, so here are some pictures. I'm going to show you one in the slides, and then we're going to do some in Python, and we're just going to do some actual repeated sampling. Okay, so if we have a distribution around the truth, this top piece is what the normal the central limit theorem tells us in the mathematics, right? We know that the samples are going to be drawn with some known distribution around the truth, and we know the distribution because of the central limit theorem. But what we actually observe is this thing. So we have some sample mean, which for this first one is 258. And then we have our sigma x bars, which then we can construct a 90% confidence interval around those things, around the x bar. So we know what the standard deviation is, and we're multiplying it by 2 and adding it and subtracting it to the mean to give us the upper and lower bounds. And we're constructing it in a way that looks like the tails will have 5% in total. So 2.5% on each side. But we're doing it not from the distribution of the sample mean, around the mean. We're doing it around the random draw. And if we do this a bunch of times, it turns out that, and I'm going to justify this to you in a second, it turns out that the mean, the truth, will be within this interval, each of these confidence intervals, 95% of the time. So this is the trick that confidence intervals in hypothesis testing sort of play on us. They reverse the logic of the central limit theorem. We're saying with the central limit theorem, 95% of the time, x bar will fall within 2 standard deviations of the truth. which tells us X bar will be within 2 standard deviations of the mean 95% of the time. Those are slightly different things. The distance between the truth and the X bar will be 2 standard deviations away from each other 95% of the time. So in some sense, what the standard, the central limit theorem is telling us is that those 2 things, one, X bar being the random variable, and mu being a non-random variable, it's just a known parameter. The distance between those 2 things is known to us. And so what we're going to do with confidence intervals is actually, instead of thinking about the distribution being around mu, we're going to think about the distribution being around X bar, because the central limit theorem tells us something about the distance between the 2 things. If we know the distance between the 2 things, we can just move the distribution from one to the other. That's the trick that allows us to know so many things about our world. So I'm going to show you some pictures, and we're just going to do some draws. But fundamentally, the central limit theorem, the takeaway here, the central limit theorem doesn't tell us the distribution around X bar. It tells us the distribution of X bar around mu. But because we know the distance between these 2 things, we can treat it as if it were the distribution around X bar. I'm going to post some notes about this. I haven't seen this communicated very clearly in many contexts, so I wrote up some notes about this. I'm going to post them to the part 3 page, just so you can sort of get a different sort of sense of why this is true. This is an intuitive trick. I think when I saw it in my statistics class, and even in grad school, I think this thing didn't click for me, that these are not the same thing, the distribution of X bar around mu and the distribution in our hypothesis testing around X bar. So I just want to I've written this out, and I want to give this to you as a little extra information about it. Okay, so essentially what we're doing is we're taking this thing, which is the distribution around mu, where we draw some X bar from the distribution, and we know X bar will fall inside this green interval 95% of the time. And we're just saying the distance between X bar and mu needs to be smaller than 2 sigma X bar 95% of the time. And we're essentially just switching this. We're saying because all that matters is the distance between these 2 things, we can then just put the distribution given to us by the central limit theorem around X bar. So we're just, mathematically, these 2 things are identical. And now we can perform hypothesis testing. We know something about the distribution of the, I'm going to fudge this a little bit. We know something about the distribution of mu relative to X bar. Okay, so this is the trick. We're going from one to the other. And the reason we can do it is because the distance between these 2 things is known by the central limit theorem, even though we can't see mu. All right. I've been talking at you for a while. Any questions about this? Why do you talk so much, Taylor? Good question. All right. It's been a wild week. I understand it's harder to focus. So should we do some Python? So I want to show you some pictures just to sort of simulate this idea and show you that it's true. So we're going to hop over to Python. I'm going to show you so this is so what we're going to do is randomly sample 100 samples and then construct a 95% confidence interval around the truth. So we know what the truth is in this example. It's going to be 50. And we know what the standard deviation is of 10. But our inference machine will not know. So we're going to check how often our samples fall within our confidence interval. So I'm going to run this, and then we'll talk about the plot. So I've drawn 100 samples. We're going to plot the mean. We have 100 samples, and I plotted each one of them on the vertical axis. And you can see relative to the mean, some of them are above, some of them are below, and they're sort of just randomly scattered around. Just like the central limit theorem, because we're taking a sample size of 30, we have a normal distribution around the mean. Just here, I've plotted the mean on the vertical axis, and then we're just looking at the deviation from the mean. The central limit theorem, you'll remember, tells us the distribution around the truth. And so what I've done is plot the distribution around the truth. So 95% of all of our samples, 95% of these 100 samples should fall within the green intervals. If they fall outside of the green intervals, I've colored them red. And then we can just check through simulation whether our samples, how many of them fall within our confidence interval. And it turns out, let's see, 5 of these fall outside of the confidence interval. And just as we predicted, right, like a 95% confidence interval should include 95% of them. And that's actually precisely what we got here. So we've run a simulation. We know what the truth is, which we don't have in practice. But because we're simulating this, we can check. And we're putting a 95% confidence interval around the truth. And exactly as you said, it contains exactly 95 of the 100 samples. This is the central limit theorem. We've already established this. But another way of seeing the confidence interval is that, so if I were to just shift this confidence interval up and place it around this upper dot, it would be red. So this confidence interval centered on the sample would include the mean the same number of times as when we do it this way. When the confidence interval is centered on the mean, it will contain the sample in exactly the same cases as when the same distribution is centered on the sample. Just the distance between this thing and the mean is symmetric, right? Like it's just, we can shift it up and it will cover the mean in exactly the same cases as when the sample is within the standard deviation. So instead of putting this is the trick. We go from this thing, which is the central limit theorem, to this next picture, which is when we move this confidence interval from around the mean to around the sample. And we check whether the sample mean, the true mean, falls within that interval. That picture looks like this. And actually, I'm going to show you the one with the red colors. So we'll run this again. And here you can see, now that we've placed the intervals around the sample means, we can check, how many of those times the truth falls within that interval. Mathematically, these two things are identical, right? One, we're putting the confidence interval around the truth, and the other, we're putting it around the estimate. But for the estimate to fall inside the confidence interval around the truth is mathematically identical to the truth falling within the confidence interval around the estimate. Any questions about this? This is the fundamental idea. These are the two pictures. All we're doing is switching from that first one, which is what the central limit theorem tells us, to the second one, which is mathematically identical, but something we can know. All right. Are you not amused? All right. So this is the basic idea. This is why confidence intervals are powerful, because 95% of the time when we run this, the truth will live within the 95% confidence interval of the estimate. All right. So very nice. And here we can see actually exactly 95% fall within the 95% confidence interval. And we can run this a bunch of times. Again, it's 95, but it won't always be. In fact, here we get it perfect. So 100% fall within the 95% confidence interval. And sometimes it will be fewer than that. We're getting some nice draws here. So we run this a bunch of times, and you can just check. We can be very confident that if we repeat this process, we're just going to get a lot of samples that are very close to the truth. So here, this one is actually less than 95%. So this is sort of the random process, right? We don't know exactly what our sample is. We want some level of confidence about if we were to repeat this a bunch of times, will the truth live on this interval? But we aren't guaranteed that the truth will actually fall inside that interval. Because we're saying it's a 95% confidence interval, sometimes the truth can live outside of it. I'd love to tell you this is what I do in my spare time in the evenings. It's not exactly. Some people just run computer simulations all the time. I've done that in a past life. In undergrad, and early grad school, I ran a bunch of Python code, and ran a bunch of simulations, which are fun. All right, so this is the idea. And if you're not amused, you must be have a heart of granite. Okay. All right. So this is a powerful tool, and this is the fundamental idea with why confidence intervals are powerful, and how we can know things about, know things probabilistically about the truth simply using sampling. Okay. So is the 95% confidence interval a good guess of mu? Well, in general. And this is the tools that we use to try to get at the truth. We can also use other levels of confidence. So, using our empirical rule, we know something about the normal distribution. If we want to be less confident, one standard deviation away from the mean. And if we wanted to be more confident, we could use more than 2 sigmas. We can be as confident as we'd like. I think in I loosely follow CERN, the Large Hadron Collider. They actually, even in physics, you have to do this stuff estimating physical constants. You actually, because everything's observational, you can get noise even when you're doing physics. And I believe they use 5 sigmas, so these very extreme tails. They're trying to be much more confident than we can be in social science, because people are noisier than particles. So we can use whatever confidence interval we like. So the way we construct these confidence intervals, we have our interval estimate, right? So going back to our picture, this is the picture I hope you leave class with. It's we have these confidence intervals around the samples, and we know the estimate, which is x bar, and then we also know the sample standard deviation, which is sigma x bar, and that's how we can get the upper and lower bounds of our confidence interval. And the way we construct these confidence intervals is using the critical value we're considering. So how many standard deviations away from the mean, and our critical value would be 1 if we're looking for the 68% confidence interval. In social science, we often use 95, and we can use even stronger confidence intervals if we like. So 1, 2, and 3 for the various confidence intervals. Okay, so if we knew the standard deviation of the population, like we've talked about, we could use that. But in practice, we use the standard deviation of the sample, our S. So the way we actually construct this confidence interval is we use the x bar, which is known to us, the mean of the sample, plus or minus the critical value, so whatever level of confidence we're looking for. And then we multiply that by the standard deviation of the sample, our S, and then we divide that by the sample size. You'll remember when we're from the central limit theorem, our distribution gets tighter and tighter around the mean when n gets larger. So we have to divide the sample standard deviation by square root of n. Okay, so this is all what we have and what we need in practice, which is amazing to me. Okay, so we have this idea here of the sort of our summary page, how we construct these confidence intervals. And this is what the confidence intervals are what allow us to test hypotheses and be some level of confident, which we're going to get to in the next class. So what we're going to do before we head out is talk through a couple examples. We'll see how far we get. Ready to do some examples? Tired of hearing me talk? Great. Love that. So let's walk through this example. So we're a rental car company, and we have a bunch of cars. So we test drive 10 Fords. So our sample size is 10, and we're wondering about the miles per gallon. So our standard our sample mean for the miles per gallon is 31.8. So this is just drawn. We take the average of all 10, and then that becomes our sample mean. But because we've observed all 10 of them, we can actually also get not just the sample mean, but also the sort of variation within the 10. So our variance is 2, and our standard deviation of the sample is the square root of 2. So we can ask a question about our data. What's the 95% confidence interval for the average miles per gallon in the fleet? So let's walk through a mathematical example, and then we'll maybe think about doing this with some code. Okay, so what's the confidence interval? We have 2 questions. We have the upper and lower bound. So here's our data. Here's our question. Is the population the population distribution of X normal? Well, we don't know what the the underlying distribution is, but we know that the sample mean is normal, and we know that by the central limit theorem. So we're going to be able to use the central limit theorem to give us some traction here. So our 95% confidence interval, because it's 95, we're going to look at 2 standard deviations above and below. So this is plus or minus 2 of our sample mean. And we know this thing. So from the central limit theorem, the sample standard deviation is going to be the standard deviation of our sample divided by the square root of n. So because we don't know the truth, the sigma, we're going to substitute in our sample mean, and that gives us this thing. We can just plug in all these numbers. Square root of 2 divided by the square root of 10. And so because we know the sample mean, we can just add and subtract 2 times the sample standard deviation to get our confidence interval. Okay, and this gives us an upper and lower bound on the miles per gallon, given that we're trying to be 95% confident. Okay. Questions about this? Did I go too fast? Should we do this in code? All right. So we have 2 numbers. Let's check whether the empirical rule, which we've just used, is equivalent to doing this precisely. And maybe we'll just show a picture here. We don't know where mu is, but we're 95% confident it's no further away from x bar than these 2 numbers. So we're 95% confident that if we were to repeat this 100 times, 95% of the time it would appear on this interval. Okay. So let's do this in code. All right, so what we'll do is go over to Google Colab, and we'll call this example 1. And maybe we'll just bring up the information we have. Okay, so let's import StatsPy, SciPy stats, and what we're going to try to do is try to construct these confidence intervals. So the thing we did in math here, we were looking for this 95% confidence interval around the truth. So maybe the first place to start with doing this, we can the first thing, we'll just put in our sample size. So n is equal to 10. We have x bar. So x bar, we could set this equal to the information we're given. So this is 31.8. And then our sample standard deviation is the square root of 2. So let's make sure we import numpy. NumPy is just the Python numbers package, and we just always call it NP just to be short. So we import NumPy as NP, and then the way we write out a square root is to do np dot sqrt. So this is sqrt. And then this is just the square root function. So we're going to put in the square root of 2. So this is square root of 2. Okay. So, I mean, one place to start in the world of large language models is to ask software like this to do some work for us. So we could ask, find the 95% confidence interval around X bar. And so it actually knows exactly what we're looking for. So I'm going to just tab this through. So I just hit tab, and that essentially auto-completed what the code was recommending for us. And this is all using Gemini, which is Google's premier large language model. And so let's just walk through what this is doing for us. This is the norm. So there's the package that's that gives us all of the things related to the normal interval and the normal distribution. And built into that package is actually a way of constructing interval estimates. And so the first entry here is 95%. So this is telling us the level of confidence we wish to be. And we're centering this interval on lock. So this is shorthand for the location of the distribution. And then we have X bar. So this is saying we're going to center it on this 31.8. And then the scale is just a way of telling the code to use the sample standard deviation using the central limit theorem. So this is, I'm going to actually pull this out. We'll call this SCLT. So SCLT. What this is doing for us, you'll remember, it's essentially just performing this idea. So we have what we know, the sample standard deviation is S, which is our square root of 2. But then we have to divide it by the square root of the sample size, which is the square root of n. So this thing is just giving us 0.447. So if we wanted to, we could actually just print this out directly. So we could print SCLT, and this will give us something pretty close to 0.447. So this thing is what happened in the slides is a rounded number. In reality, it's something closer to this. This is still rounded, just not by quite as much. Okay, so we're putting into the interval estimate the center point and then the distribution of the thing. And then what we want to do is just print this out. So this is CI for confidence interval, and then we'll print this out. And this gives us an upper and lower bound, which is slightly different. So you can check that that these are pretty similar, but they're like we've talked about. Every time we use the empirical rule, the 1, 2, 3 rule, we get something slightly different than what we do when we do this precisely in code. And the reason for that is because the empirical rule is a rounding. It's rounded to be easy to remember. It's a great tool to use on an exam. You can use it in practice if you like, but I recommend using some code. Okay, and on your homework, you're sort of asked to do these kinds of things. So getting familiar with these ideas is a good thing to do. Okay, any questions about the code here? Anyone still feeling intimidated by Python? Okay. Well, I'm going to try to convince you in the next month that you don't need to be intimidated. So this is the confidence interval. And part of what's powerful about this is doing this in code is we can actually change our levels of confidence. So sometimes you'll see in social science that we actually use 90% confidence intervals, which 90 isn't so easy to check using the empirical rule, but we can easily check it using code. So you'll see the 90% confidence interval is a tighter region, right? Like the upper and lower bounds are closer to our sample mean, which means if we only need to be 90% confident of something, then we can say something more precise. We're less confident, but we can say something more precise. And you can see this because 91 is closer to the sample mean than, 31 is closer to the sample mean than 30.9. So we've sort of moved closer. Our upper and lower bounds are tighter. And if we wanted to be even more confident, we could do like 99.7, which is our 3 sigma. And that's further away. So if you want to be more certain, you have to increase the bounds. So the upper and lower bound will contain more of the distribution if you want to be more confident. Okay. And you can repeatedly run this and nothing changes. This is not random. And all that's awfully nice. Okay, any questions about this? We have a few more minutes, so I want to introduce one more example. Next class, we're going to start using this idea of confidence intervals to do something we call hypothesis testing, where we want to not just know like a region, but we want to actually check some hypothesis. So what if you wanted to know something about a claim you might want to make, which is a common thing we do. So let's introduce one more example, and then we'll go away from here. So our second example, I talked about the changes in the confidence intervals, but you can see this in the picture. If we wanted to be more confident, we'd have to extend our intervals. And if we didn't need to be as confident, we could shrink our confidence intervals. And this is just some sort of takeaway slide you can have just to give you some sort of interval estimate summary slides. But let's look at a second example. So this is where we're starting to get into hypothesis testing just a little bit. We want to try to evaluate this a potential question we might have. So what if we wanted to check a claim? Like how likely would our how confident are we that the truth, a particular claim about the truth, is sort of close to our sample estimate. So for example, we have the same numbers. What if your manager is requiring you to buy for Avis if we need the miles per gallon to be at least 30? We have an estimate that itself is above 30, but how confident are we that the truth is actually above 30? We have our sample, which has some variability in it, and we want to be very certain that the miles per gallon is above 30. So we're asking this question: do you think the Ford fleets would satisfy this condition that the average is above 30 miles per gallon in general? So this is where we're going to go next time. Let me know if you have any questions about the Python specifically. We've done the main takeaway for today, I hope for you, is this picture from hypothesis thing, where we go from this thing to this. Stick around if you have questions about Python or the homework, and let's form our groups by the, what was it, the 19th? Yeah, just send me an email with your group, and I'll compile all those things. Yeah. Definitely.
Question about downloading Python.
Okay.
I don't know if I did it right. I did it off just like looked up Python, did a Mac download. This is what came up. I don't know, I've never used it before, so I don't know looking at.
Yeah.
Does this look right?
This isn't how I would install it.
Okay.
So in the class on Tuesday, I gave 2 different options. I don't know if you saw that.
I think I joined a little late. You didn't see that, but
Okay. Yeah, you can go back and take a look
okay.
at how to use
Check
it.
that video.
The easiest way to do it, just getting started, is to use Google Colab, which is what I showed in class.
Okay. I can go back and watch that video. That part of the video. That I think I missed, but
It's the reason it's nice is because you can just use it in your browser. You
Okay.
don't have to install anything locally.
got it.
If you end up thinking you are going to use Python in the future, having it installed locally is really nice. In
Yeah.
fact, that's how I do all of my stuff.
Okay.
But if you're not sure if it's like some work to get it installed, so I recommend people start using Google
Sorry, using like
Colab.
that. Okay.
And part of what's nice about it is you also get Gemini built in.
Oh, okay.
So all the
Yeah.
code hinting and all of that. It's
Alright,
very
nice.
nice.
I'll go back and look at that and then go through that.
Yeah.
Okay.
If you do want to install it locally, I can help you with that too.
All right. I think I should be fine. I only use it for this class right now, so
Yeah,
I should be good with that. But
yeah, that's good.
I might need it in the future. So
Yep. See you.
I have a quick question on the homework for this question.